Welcome to Unit 3, Lesson 2, Graphs of Rational Functions, Part 1, Practice Problems. I forgot to write practice problems there. Okay, so let's look at our first problem here. Jada is planning a kayak trip. She finds the expression TS is the number of hours it takes her to paddle 10 kilometers upstream. So now let's analyze. S stands for speed. The output is time. So the slope of the line is going to be distance. In terms of speed of the current, S stands for speed of the current. The number of hours, T of S, the output is the number of hours. So that's time in kilometers per hour. This is the graph Jada gets if she allows S to take on any value between 0 and 7.5. So she's going all the way out to here. Let's do this in a different color because I did this. So she's going all the way out to here, basically, 7.5. This is not appropriate. We can see that the dotted line, which will not show up on your calculators, is called an asymptote. You cannot divide by this number. So the best thing we could do is approach that point. So now, she wants to go 10 kilometers upstream. So what we're going to do is go to 10 and then go down. So a more appropriate domain to use is 0 is less than S, which is less than 4.5. I know I said 5.5 in class because that was possible, but we are limited by going 10 kilometers. Our distance is 10, so we have to draw the boxes on the graph, and we can see that 4.5 is the highest we can go. Now, if we wanted to go more kilometers upstream, obviously we could go out further. What is the approximate speed of the current if her trip takes 6 hours? So now, speed is on the y-axis, which is backwards for most graphs. But now, 6 is the time. So if her trip takes 6 hours, we come over, we touch the graph, and then we come down. We're about right here. So the speed of the current is about, 3.8, 3.7. And now we need a unit for speed. Kilometers, kph, kilometers per hour, kph. Okay, so that's the end of that problem. All right, let's read this problem carefully. A cylindrical can needs to have a volume of 6 inches, so the S is fixed. This is fixed. The label is to go around the side of the can. The function S of R gives the area of the label in square inches. Okay, so this is not volume, so this is not fixed. All right. Where R is the radius of the can in inches. Okay, so just by looking at the right side, 12 over R. As R gets closer to 0, what is the end behavior? So as R gets closer to 0, so imagine the number, R is 2, then S of R equals 6. If R is 1, S of R equals 12. So as R gets closer to 0, as R goes to 0, then the output, S of R, goes to positive infinity. So that means the area of the label grows quickly. It just grows. It increases. So again, this is an end behavior question from last unit. As R gets larger and larger, and how do we know this? Because of the graph of the function. Any 1 over R is going to look like that in the first quadrant. As R gets larger, so this question was about S going this way and the graph going that way. So S goes this way. No, R. And then S of R goes that way. So as R gets larger and larger, so let's put this in blue. So as R gets larger and larger, then S goes down, basically. So as R gets larger. So if we have 12 over R, as R gets to positive infinity, S of R goes to 0. It gets smaller and smaller. Okay, now what is the equation for the vertical asymptote? An asymptote is a line a graph can never touch. It approaches it. So how do we find the vertical asymptote? Well, what you have to do is you have to set the denominator equal to 0. So to find the VA vertical asymptote, set the denominator, that's the bottom of a fraction, denominator equal to 0. Okay, so now x minus 1 equal to 0. Add 1 to both sides. X equals 1. If I stick 1 here, 1 minus 1 is 0. We cannot divide by 0, so the answer is A. Okay, a geometric sequence H. So geometric means multiply or divide. Starts at 16 and has a growth factor of 1.75. All right, so now, so we got 16 times 1.75 to the n power. So let's multiply that out. You can put this in the y equals and get the numbers. So it starts at 16. 16 is our first term. If we start at 0 and we stick a 0 in for n, then we get there. So our first term, our second term, third term, fourth term, and fifth term. Okay, so we put this part into the calculator into y equals. We hit the y equals key. We put that in. So for term 0, we got 16. Term 1, term 2, term 3, term 4. Then there's 5 terms, though. But that's 5 terms. All right, so now, to sketch our graph, I'm going to hit 1, 2, 3, 4. Now, you have to divide your y evenly. So this is x. So I'm going to make 20, 40, 60, 80, 100, 120, 140, and then 160. I could have chosen anything, but I chose this because it'll give us a nice representation. So at 0, we're at 16. Let's put dots in blue, a different color. At 1, we're at 28, which is halfway between 20 and 40. At 2, we're at 49, which is halfway between 40 and 60. At 3, we're at 85, which is a little bit above 80. And then at 4, we're at 150, which is halfway between 140 and 160. So as you can see, it makes a curve. Well, it's supposed to make a curve graph. This is not exact, but had I drawn better, straighter lines, you would have saw the curve. All right, so now let's talk about end behavior again. Is this the graph of g of x or h of x? How do you know? This graph is of g, and how do I know? Negative x odd starts high and ends low. So do not forget your end behavior lessons. Okay, this question is from lesson 3.1, so which we didn't do. A 6-ounce cylindrical can needs to have a volume of 178 centimeters cubed. Okay, so we need to know the volume of a cylinder, which is the area of a circle times its height. The current can uses a radius of 2.75 and a radius and a height of 7.5. Use graphing technology to find a cylindrical design that will have less surface area, so each can uses less metal. So to do that, you would take either one of these down. So we could probably increase the radius and take the height down. So you had to mess with this. So basically, take the height down, and you could bump out the radius a little bit. So you can bump out the radius to about 3. Take the height of the can down to 6, and let's see what that does. So we want surface area. Surface area is a complicated equation, and so I'll write it down for you here. Okay, so the area for surface area is the area of the can side plus the area of the circles at the top and bottom. That's why it's 2. So 2 pi RH gives you, imagine a can, a cylinder, right? And you unrolled it, just this part. This part would make a big square, a rectangle. And then you got 2 circles. This is why it's 2 pi r squared, because you got 2 circles. So this is how a can would look if you unrolled it.